electron accepts hydrogen, gets reduced. Let's do it the other way. Reducing agent accepts oxygen, gives electron, gives hydrogen, gets oxidized. If you remember it this way, you will never forget it. And this is, if I say an FAD or NAD, is it oxidizing or reducing agent? NAD, what does it do? It accepts hydrogen, right? So it's an oxidizing agent because it accepts hydrogen. And what happens to it? It gets reduced when it gets formed to NADH. This is how you apply it. I mean, you should be able to figure out any oxidizing reaction or reduction reaction. So, this is the first group, which is oxidoreductase. So, there are enzymes where we say it's a reductase, it's an oxidase, and so on. So, at least you understand what's its main function. The next group, I mean, this is, I gave you an example. When you see NAD, think of NADH, oxidation. Can we keep quiet, please? Think of oxidation reduction when you see NADH, NAD. Go to transferases. The way it works. How many reactants do I have? 2. How many products do I have? 2. Most likely, there's just shuffling of groups. This is, I'm giving you the simplest tricks that you could figure it out. Where you see 2 tetrahydrofolate with serine. Now we have an enzyme, the serine hydroxymethyl transferase, forming glycine and shuttling the CH2 into tetrahydrofolate, which is one of the derivatives of folic acid. So you can see here, this is what we refer to as transferase. 2,2. If I give you a reaction where you see there's water in it, hydrolysis, so hydrolase, simple, straightforward. If I give you a reaction where we have what we refer to as ligases, example here, they catalyze, this is their function, catalyze cleavage of carbon-carbon, carbon-sulfur, and certain carbon-nitrogen bonds. An example right there, carboxy terminal, pyruvate. You can see that, the pyruvate decarboxylase, we have acetaldehyde and the release of CO2. Now, how many reactants do we have here? 1. How many do we have? 2. That's a ligase. I know this is the simplest way you could, I mean, this is like, I would say, survival for people just to figure out what's the function here. Isomerase. Isomerase should be the easiest, where there are changes in optical or geometric structure. The way you look at it, we have 1 and ended up with 1. 1 reactant, 1 substrate. So you can see that we just shuffled the reorganization of the molecule. Finally, ligases, where you have 2 reactants, you end up with 1. Let's see if what I just told you applies. We already talked about the oxidoreductase, but let's talk about the transferase. How many we have? 2. Right? This is easy. Wow. Then we have the lyase. How many we have reactants? 1 producing 2. So here we have 2. There's 1, 2. And the ligase, 2, 1. That's the easiest way. You could at least, I'm telling you, I understand this is the wrong way. But, as I said, I'm not here to make you biochemist. At least understand. When I say ligase, I'm connecting 2 molecules into 1. When I say isomerase, mutase, yes, I'm just changing the geometric configuration. When I say hydrolysis, hydrolase, I understand that I'm adding water to it. That's all I care about at this stage. Okay? So I'm telling you right now, you will get a question where I'm going to give you reaction saying which class of enzymes is this that can catalyze this one. Okay, zymogen. We know what zymogen are. They are pro-enzymes. And the way it works, this is just an example for you. Can we keep quiet, please? You can see that, in this case, trypsinogen, pro-enzyme. You can see what we refer to as the masking sequence, the blue one. The masking sequence, you can see the blue one is masking the active site of trypsinogen. When it gets secreted into the stomach, what happens? Low pH. This will cleave the masking sequence, releasing or showing, basically exposing the active site for the substrate to work. This is just an example how activation could occur. Other enzymes have different activation mechanisms. We know what the substrate, we've been talking about it, the active site, specificity, and so on. Let's start our initial introduction to the kinetics, enzyme kinetics, that we're going to have a full lecture tomorrow about enzyme kinetics.
Doctor, can one enzyme fall into multiple categories?
In what way?
So be an oxoreductase and at the same time a ligase or something?
Of course, it could. But usually we have the main function that is just basically one class. Let's get into kinetics. Just brief introduction. If we look into reaction velocity versus substrate concentration, what do we mean by substrate here? Reactants. We get chemicals, we want them to react. We apply heat. If we add more reactants, the reaction velocity would increase. So this is why we have what we refer to as direct proportional relation between the substrate concentration. As we increase the substrate concentration, we increase the reaction velocity. This is in the absence of enzymes. In the presence of enzymes, it's different. What happens is the following. This is the reaction velocity, y-axis, substrate concentration. Notice here that, first of all, tell me the slope. Compare this slope with this slope. Which one has low, which one has high slope? With or without? This is without, this is with.
This one, higher slope.
Is it high or low slope?
High.
What's the slope of a perpendicular line? What's the slope?
Zero.
0. So when you shift to the left, when you shift the curve here to here, shifting to the left, is the slope increasing or decreasing?
Increasing.
What does it mean?
Faster reaction.
Faster reaction. How? Because
More
what's the
product,
slope?
less time.
Delta x. Is it delta y or delta x over delta x delta y? Delta y over x, right? So when it shifts to the left, delta y, okay, versus delta x, you can see that what happens.
Bigger.
You learn this now. Does it decrease or increase? X decreases when we shift to the left.
Y increases. So delta Y or delta X.
What happens to y? Let's look into here. If you take two lines divided, we said delta y over delta x, right? What do you think, guys? What do you think kind of question we're going to be asking you? Whether the curve is shifted left or right? Yeah. You had this. What do you think the slope is? What's the slope of the perpendicular line, you said?
0.
0. What's the slope of horizontal line?
Undefined.
Okay. So, are we increasing the slope or decreasing the slope by moving to the left? We said 0. We're reaching to 0. But can slope go to -1? Yes, if it's the other way. But if you're moving it this way, you think you're reaching to 0, right? So what happens when you shift to the left? The slope increases or decreases?
Increases.
Increase.
Decreases when we shift to the left.
Doctor, why do you shift to the left?
When I say shift to the left, look into the line here. Now if I take this line and move it to this direction,
It's going to increase.
it's going to become all the way as perpendicular 0. Right?
No.
You know what? I'm not answering it. Expect the question.
It's the same.
I know this is the only way you to understand. First year medical students cannot figure out whether the slope is going to increase or decrease by changing the curve to the left.
Doctor, the more steep something is, the more close it is to a straight line.
Okay, I'm telling you right now.
Slope has.
Okay?
Wait.
So, when we say accelerates, what does this mean? Enzyme, guys, when I say enzymes accelerate the reactions. So, what's the definition of slope here? What is the slope?
Y over X.
Doctor, the vertical line slope is undefined.
Delta y over delta x, right?
Yes.
Is it?
Yes.
Slope.
Yes.
Yes.
Are you sure?
Yes.
We'll see tomorrow. Tomorrow we're going to discuss the slope and everything of this curve. I'm not going to waste my time now trying to find the slope. Tomorrow we're going to have, the reason I want you to know it because tomorrow we're going to be discussing all this slope and x-intercept, y-intercept. These are, can we keep quiet please? These are all parameters that we need for kinetics. Why do I care about it? Well, guess what? All these drugs will have kinetics. Can we keep quiet please? At the same time, you're working in a lab. You're trying to see what's the best condition for your enzymes. Here's the thing. If I say add ATP 1 milligram, 1 milligram is too expensive to add to that reaction. Why can't I add 1 microgram to the reaction so that the reaction will proceed? To test for this large number of patients. How do I know? Well, here's the thing. Look at the substrate concentration. If you add more of this ATP, for instance, it's useless because you already reached the Vmax. You see what I'm saying? These are all parameters we need to know. We need to figure it out. I understand we're going to have a lab and for enzymology. Hopefully we'll apply it next year because I think to understand these concepts, we will have to do it where you're going to draw the curve, the slope, and everything. Anyway, tomorrow we're going to talk about all these parameters and look it up because you will have a lot of questions. In terms with inhibitor, without inhibitors, what happens to the slope, and so on, you have to understand these concepts. So, we have what we call Vmax. What is Vmax? The maximum velocity. We will talk about the initial velocity here. This is where the initial velocity right here. Initial reaction. And we have the Vmax. What happens with the Vmax? Why the enzymes reach Vmax? We don't reach that without the enzymes. So Vmax, let's define it here. Is when the velocity that we reach, is this the maximum velocity? From the name, yes, Vmax is the maximum. But why do we reach it?
Enzymes are
Saturated active.
Saturated all the active sites, as simple as this. All the active sites of the enzyme saturated. So it doesn't matter if you want to waste more reagents by adding, for instance, ATP to the reaction because you don't need it. You already have enough for the reaction to measure it for the patient. If you were to add more, you're burning money. This is why we need to know about all these parameters. We're going to have a full lecture about it.
Doctor, do you mean to say that the enzyme is busy working at other?
No, it's saturated. I mean, basically, all the active sites. I'm going to show you the picture tomorrow. We'll look at it. So, we talked about substrate concentration Vmax. Tomorrow we'll elaborate more. However, I know that most of you are going to be confused when they look into what we refer to as the allosteric enzymes versus the enzymes following Michaels-Menten kinetics. Both with the enzyme, both basically reactions catalyzed by enzymes. However, this is the hyperbolic kind of reaction. We're going to study it tomorrow. How we can, what does it mean? And also, we're going to look into the allosteric enzymes. Anyone knows what's allosteric enzyme? What are allosteric enzymes?
There are enzymes that change the conformation of the enzyme itself. So they cause the usual substrate to not be able to bind to it.
You're almost there.
It binds to, it doesn't bind to the substrate site, it binds to another site called the allosteric site.
See, there's a lot of confusion here. Allosteric enzymes, basically enzymes that when they bind to the substrate, basically they change their conformation and they can bind more substrate with high affinity, similar to the hemoglobin. Right? Hemoglobin, when it binds to oxygen, the first molecule, it changes 3D structure, right? And then binding to more oxygen becomes easier. This is the same thing. We're going to have, tomorrow we're going to discuss the allosteric enzymes. What do they mean? How they function? What's the mechanism and so on? We will study this tomorrow. So what I just wanted to show you is that we have two different kind of reactions. Here, reaction velocity. You can see here this is hyperbolic. This is what we refer to as sigmoidal structure. And these are different enzymes. We're going to elaborate more in terms of their kinetics. So, lock and key hypothesis, I think all of you know it, right? Do I need to repeat it?
No.
Explains which group of specificity for substrate specificity? Absolute. And this lock and key hypothesis, everything we just mentioned in terms of the energy of activation, you can see the enzyme binds to the substrate, forms the ES complex, transition state. Then we have the EP, and then we have the products. When I ask you, does the EP constitute what stage? Usually it's right there towards the end of the transition stage. So, the induced fit hypothesis, we already know it, where basically the enzyme changes the 3D structure. You can see that this is not compatible with the substrate part here. So what happens? 3D changes, so we can fit the substrate into the enzyme to form the ES, then the EP, and then we have the product. This model explains which substrate specificity. That's the group model. I'm going to start asking people to walk out. Simple as this. Last one. Just to give you an example, the hexokinase we just mentioned. This is hexokinase without glucose. This is the active site. And now once there's glucose or another carbohydrate, 6 carbon molecule carbohydrate, we can see that the 3D structure of the enzyme changes, and you can see the glucose right there. Just to show you how we can accommodate multiple substrates, similar kind of structure that could fit into this group of the enzyme. Okay, you're a physician. You're going to be getting all these profiles. What kind of unit you're going to be dealing with for the enzymes? Units, or IU, international units. So what's the definition of international unit that you will get? There are 2 units, tau and U, or international units or international units. The definition for the enzyme that you will see in the patient chart, basically amount of enzyme needed to convert 1 micromole of substrate to product in 1 minute. Okay? So this is the enzyme unit. But why can't we use ketau? This is the standard unit, ketau. What is ketau? Have you ever heard about ketau?
No.
Why? So if I say to the patient, inject 5 units of insulin, would it be easier or harder when I say inject 0.005 units of insulin? So this is what ketau, because if you look at the ketau, 1 mole in 1 second. But the enzyme units, it's micromole. We multiply by million. So this, instead of expressing it as 0.00001, we just say 10 units of enzymes. Because we're already multiplying it there. That's the whole, the difference between the two units. Okay, now if you look into enzyme activity and what could affect it, we do have three factors: environmental conditions, cofactors, and coenzymes. We're going to discuss these two enzyme inhibitors. We will discuss tomorrow when we discuss kinetics and see how the enzyme, the inhibitors, especially drugs, when we say this is competitive, non-competitive, uncompetitive, we're going to look into how they could affect the Vmax. They could affect other parameters as well, and we could differentiate between these inhibitors. Why do we need to know about this? Why do we need to know about the drug, whether it's competitive, uncompetitive, or uncompetitive?
So we know how long it takes action and for how long the action stays.
Exactly, and also in case of toxicity, we could easily, what do? We know how to treat it. Right? So, if you look into the factors, we do have environmental conditions that could affect the enzyme activity. That includes temperature, pH, ion concentration. Temperature, we know that at high temperature, enzymes, proteins, denature. And this is why when someone's temperature is high, we have to take it down. Why? Because enzymes denature and we lose enzyme function. At the same time, acid-base imbalance. Have you heard about acid-base imbalance? Acid-base imbalance is very critical, very crucial condition that you have to treat within hours. Otherwise, you lose the patient. Why? Because if you change, we know that our pH is 7.4, right? But if it goes 7.6, 7.7, just small change could basically alter your enzymes, and this could lead to death. As simple as this. At the same time, ion concentration. Give examples of ion concentration that could affect enzyme activity in your body.
Salt ion.
Electrolytes, sodium, chloride, potassium. If these electrolytes are not balanced, you will end up with inactivation of the enzymes, and this could lead also to serious conditions. So all these factors could affect. Okay, in terms of the temperature, we have Q10. What's the Q10? Well, it's what we refer to as the temperature coefficient, where basically, if I increase the temperature of that reaction for the enzyme by 10 degrees, how many times I would change the activity of the enzymes? Meaning, this is the temperature, enzyme activity. If I increase from 0 to 10, let's look into the activity. Here versus here.